This is number 55D in chapter 15. It looks at calculating the H3O plus concentration, the OH minus concentration, and the pH of the following solutions. There's multiple parts. I'm just going to do the final part, part D. And so we want to know our hydronium concentration, we want to know our hydroxide concentration, and we want to know pH. And we're given some features here. We have a 0.655% nitric acid solution by mass, and we're also given that the density of the solution is equal to 1.01 milliliters. I'm sorry, grams per milliliter. And so knowing these facts, we should be able to get at our hydronium concentration, and then subsequently we can get pH and we can get hydroxide. So nitric acid, strong acid. So that means there's complete dissociation, meaning that the nitric acid concentration is actually equal to the hydronium ion concentration, because the molecule completely dissociates and immediately donates a proton to water. So really we just need to figure out essentially the molarity of the nitric acid, and then from that we have the concentration of the hydronium ion in solution. So we treat our mass percent as an assumption of 100 grams, so that means we would have 0.655 grams of the nitric acid by mass, and if we divide by its molecular mass of 63 grams per mole, we can get at the moles of our nitric acid, and again that would also equal moles of protons donated. We need to then figure out the volume of the solution. We have 100 grams of solution, and so we would use the density of 1.01 grams per milliliter to get that into terms of volume of solution. And so from there we can get at concentration. We can take our moles, divide it by our liters, and you can probably just get away with 0.099. And if we then do that, we get a value of 0.1049 molar. And so that would be our molarity for our nitric acid, but again that also means that that's also equal to our H3O plus, right? Again, because there's complete dissociation of the proton from the nitrate because it's such a strong acid. So I'm going to erase some of this, we'll come back. Okay, so again, just showing you the complete dissociation. It's really not even considered an equilibrium. So that means our concentrations that we begin with our nitric acid and our and one that dissociates are hydronium ion concentrations. Those are exactly the same. So from that we can figure out a pH, right? pH is equal to the negative log of hydronium ion concentration. So we have the pH is equal to that negative log of 0.1049, and that would be a pH equal to 0.979. So there's your pH as a result of that concentration of hydronium ion. To get at the other part to this question, figuring out the hydroxide concentration, we would have to use our autoionization of water equation to solve for it, meaning that the Kw is equal to the concentration of hydronium ion times the concentration of hydroxide. And so if we rearrange that, that our concentration of hydroxide is equal to Kw over H3O+. And so we plug that in. We have 1 times 10 to the negative 14th over H3O+, 0.1049 molar. That equals 9.53 times 10 to the negative 14th molar. And that is our hydroxide concentration. So strong acid, complete dissociation to produce H3O+, so we equate the actual concentrations initial with equilibrium, because really, since nitric acid is such a strong acid, it's really just complete dissociation. We figured out the concentration of H3O+. From that, we can get our pH. But also from that, we can get our hydroxide concentration using the Kw. An alternative way to solve this would be to use that expression. So once you solve for the pH, you could have solved for the pOH and then gotten the hydroxide concentration from there. Either or, both work. And that is number 55D.